Okay, so good morning, good afternoon, or good evening, and welcome to this webinar, which is organized by TC20 of ICG. And the idea of this webinar is to celebrate the International Year of Glass. So today we have the great pleasure to hear Professor Tanabe, who is professor at the Kyoto University and is a well-known expert in any kind of rare earth doped material, laser, amplifier, phosphors, and so on. And he was awarded many prizes, so I can't give the list of all the prizes he received. As I talked about the International Year of Glass, I just want to mention that he's a chair of the Japanese Committee of United Nations of International Year of Glass. So please, Setsu, enjoy our vision on the rare earth doped glass for the next minutes.
Thank you very much, Wilfred. Yeah, it's my pleasure to join this series of webinars organized by TC20. I've been a member for 20 years of TC20 of ICG. So today I would like to talk about fundamentals of rare earth and doped glasses photonic applications. Yeah, and first of all, this year is a United Nations International Year of Glass. This was achieved by the effort of many people of ICG, Community of Glass Association, and ICON. It was approved last May 18th at the General Assembly of United Nations in New York. So many people are delighted to hear about this news. What is a United Nations International Year? It started since 1959. There are several international years about children, and you may know 2005 was a physics and centennial anniversary of Miracle Year of Einstein. And 15 was International Year of Light and Light-based technologies that also have various milestones. And 3 years ago was a periodic table celebrating 150 years anniversary of Mendel's discovery of periodicity of the atomic elements. And this year is the International Year of Glass. So before I'd like to introduce historical topics in photonics, especially glass-related photonic technologies. The first laser we obtained was in ruby laser doped in transition metal, chromium transition metal ion, invented by Mayman. And that was using single crystal, not glass. But just 1 year later, first laser glass was invented by Dr. Eli Snitzer, working for American Optics then. Neodymium was the luminescent center of the glass laser. And he achieved amplification in neodymium doped fiber lasers, which is really surprising at that time, before the realization of optical fiber network. And he also invented Erbium doped glass laser working at 1.54 micron, now today's telecommunication wavelengths. In parallel, there was a development of a laser diode, CW operation, room temperature CW operation was achieved 1970, and he utilized the laser diode for amplification in fiber laser. And at the same time, low loss optical fiber was reported by Corning, Bell Labs, and world competitions, research competitions started worldwide. And in 90s, ultimately low loss optical fiber working at 1.55 micron was invented, NTT Group, which utilized vapor axial deposition method. The ultimately purified low loss optical fiber was achieved. And Southampton Group, Dr. Payne led, the amplifier operation in Erbium-doped silica-based fiber, he reported using by argon gas laser, which is very big. But Dr. Nakazawa of NTT utilized very compact laser diode pumped practical EDF device was invented. And also, Dr. Oishi of NTT invented praseodymium doped fiber amplifier working at 1.3 micron. And there are many, many stories, but I cannot introduce everything. But anyway, many of these active devices, lanthanide 4F electrons play crucial roles. And what are 4F orbitals? There are 7 different kinds. This is a wave function of 7 4F orbitals, which I will explain later. And in the many phenomena, optical phenomena, photon absorption, which is absorption photon, electron excited from the ground state to upper excited state, or emission, luminescence, spontaneous emission, or induced emission, which is the source of laser, light amplification by stimulated emission radiation, which is exactly the same principle for optical amplifier now utilized worldwide for long distance telecommunication. And in 19th century, Dr. Ångström investigated the emission spectrum of hydrogen and in the field in the glass tube at the high voltage pressure. He observed this discrete spectrum in 90s. And several scientists tried to explain why this kind of discrete spectrum is observed. And Balmer, who was a mathematician, not physicist, find out this simple integer relation is observed for wavelengths of observed spectrum. And Ludwig it proposed the concept of wave number, which is the inverse of wavelengths, and they derived this kind of equation, which is observed in visible region. In addition to visible region, Lyman observed deep UV region, and Paschen observed near infrared region, Brackett observed mid-infrared region, which follows the common integer relationship of the atomic spectrum. And in the early 20s, after the discovery of quantum theory by Planck, Max Planck, and support by Albert Einstein, Niels Bohr utilized the concept and finally succeeded to explain the origin of discrete spectrum, because the energy level of hydrogen atoms are expressed like this. So the inverse of integer 1, 2, 3, 4, it corresponds to the energy level of each XIA level, which now we know corresponding to the principal quantum number. But at that time, the real nature of electronic orbital was not really correct. Erwin Schrödinger introduced the concept of wave function and explained the wave properties of particle electron behaves. And he introduced the Schrödinger equation and introduced a concept of wave function composed of radial part and angular part, and explained fully the atomic orbitals, which we now understand. So this is a Schrödinger equation of 3-dimensional containing kinetic energy part and the potential part, which is a spherical potential because of the positively charged nuclear and spherical, and which has eigenvalue of energy total. And in order to solve this equation, a conversion of this Laplacian from Cartesian to polar coordinate was necessary, which becomes a little bit complex, and the derivation from Cartesian to polar coordinate takes a little bit time. But anyway, we can convert the Schrödinger equation in this like form. And substituting the psi wave function into a radial part, large r of small r, and angular part, large y, which is a function of theta and phi, we can convert this equation like that. And yeah, divide both sides by large r, large y, and transform into this shape. And we can divide the r function and theta function, resulting in this equation. So the equation, which is a function of small r and which are a function of theta phi, cannot be equal unless they are a non-dimensional constant, which is an eigenvalue, lambdas, let's say. So in order to be this equation, so this relationship must be satisfied. And for this part, Legendre polynomial need to be introduced. And final results, yeah, you see, I skip many parts of this. This is the equation number. It takes 60 minutes to reach this function shape. And the wave function is composed of radial part and angular part, and including Legendre polynomial and so on. And second, including principal quantum number n, and azimuthal quantum number L, and magnetic quantum number ML, need to take integer value correspond to this condition. So magnetic quantum number can take 2L plus 1 kind of integer from minus to positive. So radial wave functions can be corresponded to each combination of N and L are expressed like that by utilizing normalized distance, small r. Rho is a converted radius of the electrons. And this contains principal quantum number n, but after introducing this normalized rho, the form of wave function looks very simple. And it is composed, finally written like using Lagrange polynomial, which is a function of both n and L, and having n minus L minus 1 function, and which corresponds to number of nodes of the wave function, radial wave functions. And this part is a common, E minus rho over 2. So this vanishes 0 at r equal infinity, which is a common feature of wave functions. And also this part corresponds to rho, L's power of rho. So that indicates the vanishes at the nucleus, original point of the coordinate. So this is the radial part of the wave function, function of small n and n. And this, depending on the combination, this is the radial part as a function of normalized wave function. 1s orbital is like this, and 2s orbitals like this, one node, and 3d 2p orbital vanish at 0 at the nucleus. And this is a 3s orbital having 2 nodes, and 3p0 has 1 node like this. So the sign of wave function changes once. So now, so this indicates that for 1s, 2p, 3d, 4f orbitals, no node exists. Yeah, and 1s no node really exists. And for 2p, 3d, 4f orbitals, one node exists only at nucleus. That's a different point. You are used to see the s orbital always spherical because the angular part large y is a constant, not a function of theta and phi. And on the other hand, 2p has an odd parity, Ungerade symmetry like that. And having 3 functions for the combination of angular wave function, which is expressed by spherical harmonics. So corresponding to L equal 1, meaning the p orbital, magnetic quantum number can take -1, 0, +1, 3 kind of integers. And depending on the combination, the angular part becomes like this. As a result of that, 2p orbital has a 3 different kind of orbitals. And as a combination, you know, px, py, pz orbital. Actually, pz corresponds to y10. But px, pi orbital linear combination of 2 different y. So this to make the function to real number function, not imaginary function. And this is a case of d orbital corresponding to L equal 2. So a magnetic quantum number can take 0, ±1, ±2, 5 solutions. And depending on the combination, d orbital exists a different kind of angular shape like this, which is Gerade symmetry. I mean, the inversion against the original point, which is the nucleus, the sign of wave function do not change. This is called Gerade symmetry. And yeah, this probably you are used to see. This is a z square function, dx square minus y square, dxy, yz, xy function, xz function, which are Gerade symmetry because the azimuthal quantum number is 2, even number. In that case, symmetry becomes Gerade, unlike p orbital or f orbital. And depending on the combination of principal quantum number, energy level of each orbital are located like that. And precisely speaking, each energy level are not completely degenerated for the atoms having more than 1 electron. So depending on the L equals 0, 1, 2, 3, corresponding to the SPDF orbital exists. These are called subshells. And depending on the number of principal quantum number, the number of atomic orbital are expressed like that because each L different magnetic quantum number of 2L plus 1 exists. This summation becomes n squared. So the atomic orbitals with n principal quantum number can take 2n squared numbers of electrons as a result of summation of these numbers. So each orbital can accommodate only 2 electrons having the opposite spin quantum numbers. So as a result, helium can accommodate only 2, and the second period, neon 2 plus 2 times 2 square equal 8. So atomic number of neon becomes 10. Third period, does not correspond to plus 18, which is a 2 times 3 square. But atomic number of argon, which is the last rare gas element of third period, is 28 instead of 36. So that is due to no 3D orbitals are occupied yet. This is the situation. And because that, yeah, for the F orbital corresponding to L equals 3, 7 solutions exist. So function becomes much more complicated, but odd parity, so which is called Ungerade symmetry. So sign of wave function becomes inverse as a function of inversion. So this is these are the 7 4F orbitals. So node exists only passing at the original point. So yeah, this is a feature of the F orbitals. And as a result of that, we can see the atomic number of the 18th group, which is the rare gas element, can be derived like this, 2, 10, 18, 36, 54, 86. So there is no need to memorize atomic number if we remember such a kind of beautiful features. So 3 years ago was 150th anniversary of periodic table proposed by Mendeleev. So it was proved to be an international year of periodic table, which IUPAC, International Union of Pure and Applied Chemistry, proposed that, and through the UNESCO General Assembly of United Nations approved that. We celebrated this the treasure of periodic table. So how can we consider the electronic configurations, atomic elements? Aufbau principle, we can understand the atomic configuration. Yeah, which means the electron are occupied from the lower energy orbitals, starting from 1s, 2s, and 2p, and 3s, and after that 3p. And before filling 3D orbital, 4s is once filled. And transition metal series starts the fourth period, 3D. After that, 4p is filled. After that, fifth period starts from 5s orbital. And before 5p, 4D orbitals are filled, which is again the transition element series. And 5p, and the sixth period will start from 6 electron orbitals. Before filling 5D orbitals, 4f orbitals are occupied, which is more stable than 5D orbitals. So the energy of 7 4f orbitals can be understood located to around this levels. So Aufbau principle explain how the atomic electronic configuration of each elements are. And this is again the periodic table, which is a very special periodic table expressing the value of electronegativity. Yeah, we can see s orbital, p orbital, and 10 lines of d orbital, and f elements are located here, which is not actually the case, but outstanding 15 elements, 14 elements are located here after the Lanza number. And these, among these elements, except lutetium, which is fully, the 7 4f orbitals are fully occupied, cerium to ytterbium, 13 lanthanoid elements are optically active by 4f orbital, which accommodate up to 14 electrons. And we need to remember the last atomic elements rare gas xenon has 54, well, the 54 is xenon's atomic number. And xenon is terminated 5s2 and 5p6, which has larger radial wave functions of wave function than the 4f orbital. Because of that, 4f orbitals are shielded by 8 5sp electrons, which is important features of optical properties of due to 4f electrons in lanthanide elements. So we can consider the electronic configuration of lanthanide elements, 15 lanthanide elements, starting from lanthanum 57 and cerium 58 and praseodymium 59. And yeah, in the middle is a gadolinium 64, having 7 4f electrons. Instead of having 8 4f electrons, he prefers to having a half-filled state and put 1 electron into 5D orbitals. This is very unique feature, which is also observed in chromium in 3D transition metal elements. And similarly, field. And last, lutetium, because 15th electron cannot be accommodated into 4f electron, it must be occupied in 5D orbitals. But after 3 electrons are removed to be a trivalent state, the number of 4f electron is expressed like this, which is atomic number minus 57. 57 is composed of course, 54 electrons corresponding to xenon, and 2 6s electron, and 1 4f electron or 5d electron. So there is no exception about the number of 4f electrons in all the lanthanide trivalent lanthanide elements. And energy splitting for multi-electron system can be understood like this. First, Coulomb interaction split most largely, and spin orbit interaction split into triplet state into three different J state. And finally, crystal field splitting gives Stark splitting in the case of lanthanide. So crystal field splitting is smaller in 4f electron compared with other typical elements. So what happens for 4f2 electronic configuration? This is P2 configuration, which is different. In the case of praseodymium 59, trivalent of which has only 2 4f electrons, the total spin becomes 1 unity, so triplet state. And total angular momentum becomes 5, corresponding to alphabet H. And total quantum number J equal L minus S become more stable, becomes 4. So this electronic state is expressed triplet H4, which is a ground state of trivalent praseodymium ion. If 1 electron are located like this, so total spin number becomes 0, and L equal 4, corresponding alphabet G, and total quantum number becomes 4 minus 0 equal 4. This is called singlet G4, which has excited state having 10,000 wave number corresponding to 1 micron wavelength excited state. So praseodymium ion can absorb 1 micron photon and emit 1.3 micron photons, which is a wavelength of second telecommunication window, transition of praseodymium doped fiber amplifier. So the spectral shape depends on how the Stark splitting happens depending on the host, local structure of the host material. And this is the absorption spectrum of praseodymium doped glass. And y-axis, I took wave number instead of absorption coefficient or wavelengths. Opposite wavelengths is, inverse wavelengths is plotted here. And absorption coefficient for x-axis. So we can see the corresponding energy level excited state, absorption excited state can be estimated. So wave number can be a useful energy unit than joule or electron volt, and more easily converted into wavelengths. So this is the energy level diagram of 13 lanthanoid trivalent lanthanoid elements having 1 to 13 4f electrons. Cerium has 1, Erbium has 13 electrons. Among them, there are luminescent center of blue, green, yellow, orange, red in these elements. And Erbium and neodymium are luminescent center of near-infrared lasers. And also, for telecommunication wavelengths, praseodymium 1.3 micron, thulium 1.4 micron, Erbium 1.55 micron transition is like this. Except Erbium, praseodymium, thulium are 4-level system, and Erbium 3-level system. And this is a comparison of praseodymium or thulium or Erbium doped telluride glasses having a rather large, broad bandwidth compared with silica host glasses. So many of the luminescence are composed of FF transition, which are shielded by 5s and 5p electrons, and many visible luminescence from terbium green, europium 3+ have a sharp feature. This is not rare. This is actually a mercury line of fluorescent tube. Fluorescent tube 254 nanometer UV light can efficiently excite the phosphor materials developed for this purpose of fluorescent tube. So because of this, the offset of the excited state are not different from that of ground state. The sideband having a different vibrational state have equal energy. As a result, the transition shape becomes very sharp for FF transition, as you can see. For this is europium red, this is terbium green. And there is no strong blue excitation band, and the FF transition are reported forbidden. And there is no trivalent atomic elements which can be excited by FF transition. The exception is cerium. I will talk about it later, but not now. So this is an optical loss spectrum of silica-based optical fiber developed. In the short wavelength region, Rayleigh scattering, which is proportional to the inverse force power of wavelengths, are dominant. And longer wavelengths, multi-photon absorption becomes dominant. And because of that, 1.55 micron region is the lowest minimum loss wavelength resources, which coincidentally overlap with the raising wavelengths of Erbium. So this is a Coulomb interaction of Erbium levels, quartet I, quartet F, and quartet S. And important is the ground state, quartet 15½ and the first excited quartet 13½ level, which has Stark splitting into 8 or 7 components. And that is utilized for the emission at 1.5 micron region. And utilizing by exciting to the second excited state, is that second excited state, which is quartet 11½ level, quickly relaxed into the post-excited state by multi-photon relaxation because of the small energy gap and because of the very stable excited state of qualitative I13 half level, it has very high quantum efficiency emission is observed, as well as green up conversion, which is a result of two-step excitation into upper state. But this works, and actually this is propagation length of optical telecommunication. Signal is decreasing exponentially by Rayleigh scattering and several reasons, but intermediate base optical amplifier can work to amplify 30 dB or 40 dB to amplify the signal. So signal can be amplified by the same phase at the same wavelength, and also parallel amplification is possible by stimulated emission of broad of Erbium doped glass fiber having a broad emission spectrum. And that is pumped by WDM coupler with a 980 nanometer or 1480 nanometer laser diode, which excite second and first excited state respectively to achieve the population inversion in Erbium ions. And depending on the glass host material, amplifier band is different. Silica has a rather narrow amplification band, fluoride broader, and telluride much broader to longer wavelengths. So once telluride glass might be good host material for broadband wavelength division multiplexing, and the spectrum depending on the local atomic structure around Erbium ions in glass. And and intrinsically, amorphous material often gives the inhomogeneous broadening, even though the singlet not splitting structure, that is often the case. As well as that, because of the Stark splitting, the spectrum of Erbium non-zero J Stark splitting gives this complex splitting spectrum. And EDFA is made of silica-based glass, or sometimes telluride maybe, or fluoride maybe, having different that. And parallel amplification is possible, and combined with time division multiplexing, high capacity telecommunication is achieved. This is a comparison of old-fashioned telecommunication and WDM telecommunication after the invention of EDFA. So by WDM coupled into 8 different channels into one fiber, and because of the large gain of amplifier, the number of intermediate base can be decreased. So the system becomes much more simplified by the development of Erbium doped fiber amplifier, and dense WDM becomes possible. And this energy level becomes the symbol of the international workshop on photoluminescence of layers, which was initiated by Dr. Giancarlo Rigini, Maurizio Ferrari, and starting at 2005. And after 3 workshops in Italy, I accepted to organize once in Japan, and I organized Kyoto in 2012 in Kyoto, expecting the cherry blossom, but that was not the case, unfortunately, only this year. This is the scientific committee. This is a flag event of TC20 optoelectronic glass. Now the name of the TC changed into photonic glasses and optical fiber. That is the present name of TC20 of ICG. These are the committee members. This is a little bit already 10 years ago. So this is, or now the member is renewed a little bit. So laser is optical amplifier, and the worldwide undersea cable enabled worldwide telecommunication connection with WDM system enabled by EDFA, and metropolitan network enabled by EDFA, fiber to the form becomes possible for division. And this is a amplifying wavelength region of various lanthanoid elements based on the decay diagram. Among 13 lanthanoid elements, 5 or 6 ions shows luminescence band in the near-infrared telecommunication wavelength region. So because of especially invention of EDFA enabled the present long telecommunication, large capacity telecommunication becomes possible. And this is an example of 1.3 micron, which is called O band, original band, and S band, shorter than conventional band, exists here. And comparison of O band, S band, C band emission by these lanthanoid elements shown like this. And this is the name of the telecommunication band. And longer side called L band, and ultra long side called U band, which very good amplifier not yet really developed. Yeah, there is a candidate. Yeah, this is a comparison of energy levels. These are the candidate of 1.3 micron, praseodymium, neodymium, dysprosium. Dysprosium can work only in chalcogenide glass or halide crystals having very low photon energy because of the very narrow energy gap. So quantum efficiency cannot be high even in the fluoride glass materials for dysprosium. So at the same time, there was a development of light-emitting diode and laser diode. Laser diodes are very important for the information transceiver. And also, yeah, so depending on the 3-5 group semiconductor, and indium phosphide single crystal can be used as a substrate of the growth by chemical vapor deposition of the mixed alloy solid solution, which is a compound of indium gallium 3 group 3 and arsenide phosphide group 5, 3-5 group semiconductor, and the band gap can be tuned in this region. And pure phosphide can achieve visible light emitting diode, and actually green LED was developed in phosphide material, and red LED also in phosphide material. But no blue LED was developed until early 1990s. So before that, up conversion was considered to be an interesting method to obtain blue lasers. And yeah, this is an introduction of TDFA, which is S-band, 1.4 micron region, up to 1.52 micron region. I was doing this amplification experiments already 20 years ago by utilizing tunable signal laser diode and slim dope fiber, fluoride fibers, and measuring the gain spectrum by dual wavelength pumping scheme was very efficient, which is a kind of up conversion, because the population inversion between the third excited state and the first excited state was very difficult. This excited state absorption pumping was necessary to achieve population inversion, which is necessary for signal amplification. And this is a comparison of gain spectrum of TDFA with EDFA. You can see the gain band is separated. So WDM becomes possible by combining TDFA as well as EDFA. More wavelength resources can be utilized. And this is necessary. Utilizing low photon energy glass is necessary because the in the initial level of 1.3 micron or 1.4 micron luminescence in praseodymium or thulium has very narrow energy gap to the next lower level. And this is a dependence of the multiphonon decay rate as a function of inverse phonon energy, following the Miyakawa-Dexter law. So praseodymium suffers from high multiphonon relaxation. Compared with that, thulium has less because of a little bit larger energy gap to the next lower level. Instead, the slope becomes a little bit steep. And this is a comparison of phonon sideband spectrum of various oxide glasses. We can see sideband around 1300, 1200, 1100, 900, 750, 100 wave number region. Higher side of the pure electronic transition, which is actually the quintet D2 excited state of europium. This is most usefully photon sideband can easily be observed in the case of europium. So we check the compositional dependence of phonon sideband in various oxide glasses in this case. And I also worked on a blue up conversion material in Kyoto University when I was a very young assistant professor. And after that, I took a sabbatical of 1 year at Rutgers University of New Jersey because Professor Eli Snitzer was there just before his retirement. And I worked on thulium dope fiber, blue up conversion fiber. The one student was making thulium doped fiber by MCBD method for the purpose of 1.8 micron near infrared laser. But because I was working on up conversion to obtain green, I asked another neighbor professor, who is Professor George Harrington, to use his dye laser, red dye laser, to pump thulium fiber to obtain beautiful blue. So at that time, we didn't have blue LED. So I was happy to see blue emission, not lasing, but beautiful. Yeah, this is a picture at the retirement party of Professor Eli Snitzer. And his retirement party was almost the last day of my 1 year sabbatical. So this was a memorable party at his retirement party. And before that, I was working on the excited state absorption mechanism of thulium blue up conversion and published a Physical Review B in '93. I wrote like this at the introduction of this paper. A blue emitting laser is an attractive material. So I didn't know gallium nitride will be realized very soon after that. And there's nothing we consider application for the general lighting by utilizing blue light sources then. It's true, it's clear. And one application is three-dimensional color display, which has proposed a group of Stanford University. Elizabeth Downing, who was a PhD student then, presented an excellent paper in Science. So utilizing dual near-infrared laser pumping, RGB can be achieved, luminescence achieved only at the crossing point. So color display pixel, three-dimensional color pixel can be possible. And there is a three luminescent center, praseodymium for red, erbium for green, and thulium for blue. The important thing is we shouldn't pump by one wavelength, but we need to utilize two different infrared wavelengths in order to achieve three-dimensional display. But anyway, this can be possible. And Yeah, some student at Rutgers University then was collaborating supplying fluoride, doped fluoride glasses and collaborated then. I remember that. And these three luminescent center, blue, green, red, happen to correspond to the telecom amplifier, although the order is different. Praseodymium 3 O band, thulium S band, Erbium C and L band. So the order is different. So happen to be the intermediate level is for up conversion is the initial level of telecom amplification near infrared transition, you can see. So I don't know who before me who might have noticed about that, but I didn't find any references. I noticed about that, and I wrote this on a paper which was published in 2015 at the special issue of International Year of Light. At that time, Professor David Pye, who was president of ICG and American Science Society, and founding editor of the International Journal of Glass Science. And he edited the special issue of International Year of Light and Glass and Light. And I was asked to contribute a review paper. First, he asked me, please write a review paper, Glass and Light. No, it's too wide, I cannot write. So maybe Glass and Layers, I may be able to contribute. So I wrote, I forgot, maybe 20 pages of review paper and submit and accepted. That was IYL 2015. And after the development of near-infrared and red phosphide laser and green LED, nitride blue LED was developed. Initiator was Professor Akasaki of Nagoya University. Amano was an undergraduate student and a PhD student. And following that, Dr. Nakamura developed much high quality crystal growth in CVD. And finally, indium gallium nitride and PN junction was achieved. He also achieved laser lasing. Blue laser diode was achieved, which is now the standard wavelength of Blu-ray disc worldwide, which is a high density optical memory. And combination with yellow phosphor, Nichia company, not a colleague of Dr. Nakamura, Dr. Shimizu, invented white LED. So power illumination by solid state lighting was initiated, compared with vacuum tube lighting. So white LED or LED source plays a very important role to achieve solid state lighting. This is a wavelength variations of external quantum efficiency of nitride LED and phosphide LED. You can see nitride has high quantum efficiency around 400 to 450 nanometer, blue region, and not green by increasing indium content, narrowing the band gap. In the case of phosphide, aluminum-rich composition, indium-rich composition has a high quantum efficiency, but widening the band gap, approaching to orange-yellow, quantum efficiency drops. Instead, human eye sensitivity has this kind of curve, peaking at 555 nanometer. Easy to remember. Eye response is like that. So we call it green gap of semiconductor. So nitride, either nitride or phosphide nitride LED has very low quantum efficiency at the green region, which is most sensitive for human eyes. Based on this situation, phosphor-converting into downshifting from blue to green, yellow, red can be a smart method to achieve a generation of white light spectrum. This is an example of combination of blue LED and yellow phosphor, which is actually YAG-cerium. Yellow phosphor, but because of the reasons explained below, has very broad emission spectrum, covering wide visible range, different from europium 3+ and terbium 3+, which is utilized in fluorescent tube. But this phosphor has very broad luminescence, covering wide. And good thing is there is no infrared emission, unlike an incandescent lamp or violet UV region, unlike fluorescent tube. So spectrum exists only in visible wavelength region. That is a good point. And YAG-cerium, which was actually known 1960s by Professor Brasse, Utrecht University. He invented YAG-cerium yellow phosphor, utilizing very strong blue absorption. This is an excitation spectrum peaking at 460 nanometer due to 4F5D transition, which is Laporte. So very large absorption cross-section. At the same time, due to the source shift, luminescent appears at little bit longer wavelengths because of the broad 5D 4F transition. And this is a local structure of garnet crystal. And this yttrium site, YAG yttrium, aluminum garnet, yttrium site, dodecahedral site can accommodate any kind of lanthanoid elements. And octahedral site can accommodate scandium or aluminum or gallium. Tetrahedral site can accommodate gallium, aluminum, and sometimes silicate material. And after the invention of blue LED, Dr. Bando Shimizu invented white LED by utilizing YAG-cerium phosphor. Actually, Nichia company was originally a small phosphor company, not a LED company. Dr. Nakamura independently has started the research and developed gallium nitride LED. And their colleague utilized. So in a sense, this was a marriage of YAG-cerium with blue LED to achieve the white emission. And this is a resultant spectrum of white LED. You see, if you eliminate under white, it looks yellow, under blue, UV looks yellow, under blue, it looks white. So combination with that. And this is the explanation why 45F luminescence has broad absorption band and broad emission spectrum. Because of the large radial integral part of the wave function of 5D orbital, the principal quantum number is larger than 4F, 5. So the offset is shifted to longer side. So, bond equilibrium minimum energy point becomes longer than that of the ground state. As a result, this is really exaggerated too much, but there exists a gap variation of emitted photon energy, resulting in a very wide emission spectrum like this. And then color coordinate is very important for evaluating the visible lighting sources. And because human eye are composed of like this, and lens is here, and at the retina, there is 3 different cone cells, which has different wavelength sensitivity. Because of the combination of that, two-dimensional CIE chromaticity diagram was developed at 1932. So we evaluate the color coordinate with this two-dimensional because we human beings has only 3 different cones. So color coordinate can be expressed in two-dimensional format. And also, yeah, this is from textbook. There are a lot of allowed transition, delta equal plus minus one. One thing is missing, 5D4F here. So this should be added in new textbook because many important phosphors like cerium 3 plus or europium 2 plus utilize this important transition, having large absorption and emission cross-section like this. And this is a comparison of white light source, sunlight containing UV and near infrared, halogen lamp, incandescent lamp, has a majority near infrared. This is fluorescent tube spectrum, as I explained. Mercury line downshifted to green and red. And of course, they utilize blue phosphor also. But this is not phosphor, but mercury line, 440. Compared with that, blue LED phosphor converting LED has very small Stokes shift. So energy loss is very small. And even near UV LED pumped RGB LED, which can achieve better color rendering index. Also, although less efficient than blue LED-based white LED, compared with fluorescent tube, very efficient, and no waste in infrared and a little bit waste in UV region, but much better than halogen lamp, you can see. So the role of phosphor in phosphor converting white LED is a redistribution of high photon energy into lower photon energy by phosphor materials, downshifting. And YAG can be made into transparent ceramics. And it's good to compare the transmission spectrum instead of reflectance spectrum. This is the inline transmission spectrum. You can see 406 is a peak, 330 is a second 5D excited state. And color coordinate can be tuned between blue point of LED and that of YAG cell, yellow point, having this broad emission. So depending on the thickness of the ceramic phosphor, we can choose the color coordinate between this region, bluish white to yellowish white. So among various ransomware elements, FF transition does not allow the efficient absorption excitation, but instead, cerium has excited 5D orbitals in garnet host material. Garnet gives the largest crystal field splitting for cerium 5D orbital. And good thing is FD transition is rapport allowed. So very efficient excitation by FD absorption transition and large emission cross-section of short lifetime. Maybe typical excited lifetime of FF transition may be millisecond or 100 microsecond, but that of YAG cerium is 50 nanoseconds. So efficient large emission, spontaneous emission probability is achieved in YAG cerium phosphor material. So color coordinate in YAG cerium is like this. Plotted here is called Planckian locus, and temperature here is a black body radiation temperature. And you know, the temperature dependence of black body radiation spectrum changes like this. Peak wavelength is inversely proportional to the absolute temperature of the black body. So this is called Wien's law. And actually, if we plot the color coordinate of black body radiation spectrum, low temperature looks orange, 3000 Kelvin correspond incandescent lamp, whitish orange, and 6,000 Kelvin is very close to pure white. Pure white means X equal Y equal 0.33, pure white. YAG cerium has a little bit large Y value than X value. So we cannot achieve real true white, but that can be achieved by choosing the gadolinium substitute the garnet crystal. And this is a temperature dependence black body radiation proposed Max Planck, which is a trigger of quantum theory. The initial 20th century, 1900. Photon has energy unit which is proportional to the frequency nu. And he didn't say H as a Planck constant. Somebody else called Planck's constant. He didn't like H to be called like that. Fine. And this theory was soon supported by Albert Einstein 5 years later, his famous paper of photoelectric effect. And International Year of Physics is actually the 100th anniversary of the miracle year of Albert Einstein, who wrote 3 important papers, which is important for the development of modern physics. Yeah, and this is, sunlight is corresponding to the black body radiation about 5700 Kelvin. Sorry, this is the same. And tuning of cerium emission spectrum can be possible by substituting a yttrium site of YAG with gadolinium, larger gadolinium, which gives red shift, a smaller lutetium, which gives blue shift. So this is a picture of YAG yellow and gadolinium changing orange, lutetium substitution changes greenish yellow. So actually the crystal field splitting is really visible in cerium doped garnet materials, you can see. And another substitution of octahedral and tetrahedral site also gives spectral shift of the cerium excited 5D state. And most important is the lowest 5D1 excited state, which is the initial level. And actually, gadolinium substituted garnet gives a orangish yellow, and which makes possible pure white as well as warm white, corresponding to 3000 Kelvin black body color coordinate, close to incandescent lamp, although the real spectral shape is different without including infrared light. That is possible by utilizing that. So solid state lighting technology utilizing phosphor-converting LED or laser diode are considered much more efficient than LED-based lighting. So anyway, downshifting by inorganic phosphor is very promising technology to achieve efficient lighting, and several research are going on still. And because of the importance of LED lighting, the 3 Japanese inventors, Akasaki, Amano, Nakamura, was awarded the Nobel Prize in Physics 2014. And this is a ceremony which is just 3 weeks before the starting of International Year of Light 2015. So that's very interesting. I suspect Nobel Committee considered about next year is a IYL. So that's why I don't know. And YAG cerium was invented in Brasse, and Dr. Shimizu utilized this phosphor to combine with the blue LED, very strongest LED invented by Nakamura, by Nichia company. So we did a little bit different approach for the solid state lighting. We developed glass ceramics precipitated in YAG cerium nanocrystal. In this case, matrix is silicate glass, which has much better durability and thermal resistance than silicon or powder. This is a picture of as-made glass containing cerium after ceramization, which has the same color as YAG cerium phosphor, but much more strong. silicate-based host material. And yttrium aluminum containing silicate glass has much stronger mechanical strength. And we invented 2004 and reported 2006 and proceedings 2005 at SPIE. There was a conference on solid state lighting, which is newly evolving age. At that time, luminous efficacy of white LED was lower than fluorescent tube, but many people were trying effort about that. And at the year of International Year of Light, David Pye proposed a special issue, Glass and Light, and we are also asked to contribute glass ceramics and solid state lighting. Dr. Fujita was a collaborator with me. And this is not the surface cover of this special issue, but as a previous issue, our ceramics was taken as a top page of the cover. Oh, anyway, I would like to finish here and celebrating International Year of Glass. Thank you very much for your attention, and any questions are welcome. Thank you very much.
Thank you, Tetsu.